Hello friend, welcome to the lecture. Here we continue our discussion which we have started in previous lecture. So, what we have seen in previous lecture that this existence and uniqueness theorem which we have considered is a local existence theorem, and it only discuss the existence in a small neighborhood of initial point, and that we have seen using one example, that is y dash equal to y square with the initial condition y0 equal to 2. It means that we have considered this y dash equal to y square and y0 equal to 2. Here we have shown that solution actually exists in a larger interval, but if we use our existence and uniqueness theorem, and then this interval is quite small, that is given as modulus of t less than 1 by 8. So, here this says that our theorem is a local existence theorem which gives solution only in a small neighborhood of initial point. And the proof of the this existence and uniqueness theorem requires the ellipsis continuity of the nonlinear function even when we only required existence of the solution. So, for this will give not only existence, but also guaranteed the uniqueness of the solution. But if, in some cases we need only the existence, there this is a kind of strict theorem. It is requiring a lot of more thing. So, in this regard the existence of a solution, this theorem 1 is not the only and best result. We have one more result which is which gives the existence of solution without uniqueness, without guarantee, without giving guarantee for uniqueness. And what such important results we can give it right now, that suppose f is continuous on the rectangle R, and suppose modulus of f t y is bounded by some constant m for all point t y in that rectangle R, and let alpha be the smaller of the positive numbers a and b by m that we have already defined as a rectangle, then there is a solution y of the differential equation 1 that satisfies the initial condition 2 existing on the interval modulus of t minus t naught less than or equal to alpha. The only difference between this and the previous existence and uniqueness theorem, that here we have not assumed that f t y satisfies the ellipsis condition. So, here this ellipsis condition is removed. So, by removing this we lost the guarantee of uniqueness. So, here we have only the guarantee of existence, and solution may be unique, may not be unique. So, let us look at one example. So, consider the equation y dash equal to 3y to power 2 by 3, y0 equal to 0 here, and initial condition is given as y0 equal to 0, and if you look at your f t y is given as y to power 2 by 3, and we can check that it does not satisfy the ellipsis condition in several way. And if you look at you can find out the partial derivative, del f by del y t y is equal to 2 y to power minus 1 by 3, and we can also check that an indirect thing that f does not satisfy the ellipsis condition, and hence we cannot apply existence and uniqueness theorem 1 to get any result about the existence and uniqueness of the solution. In fact, that will not also give the condition that it has a solution also. So, here we observe that f is continuous in the whole ty plane, and we can apply the previous theorem, that is theorem 2, to this problem. And in fact, there is an infinite number of solution 0 0. So, since f t y is continuous, we can apply the previous theorem, theorem 2. And we can say that this f t y is bounded by if we define our rectangle in a proper way, then we can say that this f t y is continuous, and in a closed rectangle it will achieve the maximum value, that is some constant m. So, here we guarantee the existence of a solution, we may not have the uniqueness, and we have seen that in particular in this particular problem we have an infinite number of solution passing through 0 0, and we can say that for every constant c greater than 0, the function y c defined by this y c t equal to 0, 0 is between minus infinity to c, and t minus c to power 3 where t is defined from c to infinity is a solution of this y dash equal to 3y to power 2 by 3, and which passes through 0 0, and this is a one parameter family of solution. In fact, you can define two parameter family of solution of the same problem. So, it means that here not only the solution exists, but solutions are infinite in number. So, in addition, 0 function is also a solution of this initial value problem, and of course, for every initial point t naught y naught with y naught not equal to 0, we have existence by theorem 1. So, if you look at this y 0 equal to 0, this initial condition is creating problem for this initial value problem. If we remove this initial condition y 0 by some non-zero number, then we can apply our existence and uniqueness theorem, and we can say that it has a unique solution. So, if we consider y naught not equal to 0, we have a unique solution in a rectangle where y naught is not equal to 0 is a point. But if we have if we consider a rectangle where we have y 0 equal to 0, then we lose the uniqueness, and in fact, we can see that we have one parameter family of solution given by this equation y c t equal to this thing. And in fact, if you do a little bit more, we can define two parameter family of solution of the same problem. So, moving on, next we say that so what we have done, we removed the ellipsis condition on f, and we have no guarantee that solution is unique or not. But if you look at, if in addition to this assumption of theorem 2, the function f is monotonically non increasing in y for each fixed t on r, then the initial value problem 1 2 has a unique solution. So, it means that to compensate the loss, if we put one more addition condition that f is monotonically non increasing in y for each t, then we regain the uniqueness of the solution. Here will not provide any solution of the theorem 2 and this corollary, because it is a little bit involved and it requires some more advanced theory. So, we are not giving this thing, but we observe this thing that it is not possible to prove the theorem 2 by the method of successive approximation. That one thing we have to point out, that here the proof of this theorem 2 and this corollary 5 is not given with the help of successive approximation, because here as the successive approximation may not converge under the hypothesis of theorem 2. So, we can look at the following example where we will see that the condition given in theorem 2 is not sufficient to give surety for convergence of approximate successive approximations. So, let us consider this example. Consider the function f defined in the region D in the t y plane, where D is given by minus infinity to 1 and minus infinity to plus infinity, and f t y is given as 0 when minus infinity to t less than or equal to 0 and minus infinity less than y less than infinity, and 2t when 0 less than t less than 1 and minus infinity less than y less than 0. And similarly, we can define in different region the function f t y, and here we can say that f t y is continuous and bounded by the constant 2 on D. So, continuous, to see that it is continuous, you just look at the function f t y, and you can see that if we move from right hand side to left hand side and left hand side, you will get the same value. So, it is a continuous function and it is bounded by 2 on domain D. And if you want to find out the successive approximation for this particular problem, y dash equal to f t y, and we can check that the successive approximation is given by y naught t equal to 0 and y 2 k minus 1 t equal to t square and y 2 k t is equal to minus t square, and it means that all the odd successive approximation is given by t square and or the even approximation is given by minus t square, and since so that your solution is oscillating between t square and minus t square. So, and since it is oscillating, this approximation will not converge to the solution which we are searching for. So, here we can say that the successive approximation alternate between t square and minus t square and do not converge. Since the function f t y is continuous and bounded, So our theorem 2 will be applicable, and we can say that existence of a solution exists. And not only this, we can observe that this function f is monotonically non increasing in y for every fixed t, and so corollary 5 is also applicable, and this gives that we have a unique solution of this particular problem. So not only this, so here we can say that this here successive approximation do exist, but they will not converge to a solution, but still this problem has a solution, and not only that solution exists, it will have a unique solution. So how to find out this y naught t equal to 0 and y k 2k minus 1 t square? I will just show you this condition. Y dash y1 is going to be what, since y0 is given as 0 here, so here we simply say it is 0 to t and f s y of s y naught s and ds. Now since y naught is given as 0, so f s 0 is going to be here it is 2t. So here it is equality is given, so it is given as 2t, so we can say that 0 to t and 2s ds. So it is given as say t square. So here we can say that y1 is given at t square. Now to find out y2 is given as 0 to t and f of s and y1s ds. Now y1s is t square, so it will lie here. So so here we write fsys as 2t minus 4 y1 upon t. So what is this? Let me do it here. So here we have y1 y2 as 0 to t, it is 2t minus 4 y upon t dt. So here we have y1, so y1 is given as t square. So here we can write it 0 to t 2t minus 4 into t square upon t and dt. So here there is a small abuse of notation. I should write 2s minus 4 y1 upon s ds. So if you have no ambiguity, let me write it here. So here we can write this as 0 to t 2t minus, and this I can write it 4t dt, and this we can write it 0 to t minus 2t dt. So that is given as minus of t square. So please here we let us write it t1 here, so that we should not have any confusion. So here we have that y2 is given as minus t square, and we have seen that y1 is given as t square, and similarly you can calculate y3 y4 and so on, and we can observe that y naught t is 0 and y all the odd approximation is given by t square, and or the even given by minus t square. So here approximate solution will not converge to any solution, and so we cannot apply theorem 1 to find out the solution of this particular problem, but we can apply theorem 2 and corollary to find out that it has a solution, and not only the solution, it will have a unique solution. So we may conclude the following thing, that assurance of merely existence of solution does not require Lipschitz condition. So it means that Lipschitz condition is required only for uniqueness. If we drop the uniqueness Lipschitz condition, that may not guarantee whether the solution exists or not. So we can say that if we want only for existence, then we do not require Lipschitz condition. We need only continuity. Only continuity of f is required in y. So only if we require only existence, continuity of f is sufficient. Now here approximation do not converge, but still we have a unique solution. So it means that approximation solution converge and having a unique solution, these two are two different things. So it means that continuity of f and uniqueness of solution do not imply the convergence of approximate solution. So in particular, in previous problem we have a unique solution, we have but still this successive approximation solution does not converge. So we can say that their uniqueness result and convergence of successive approximation are two different independent phenomena. So it means that here it is not related. We in previous class in previous lecture we have seen that Lipschitz continuity is required for uniqueness of the solution, but here we have shown that we have a unique solution, but still we do not require Lipschitz continuity, and we also do not have the convergence of successive approximation. So we say that convergence of successive approximation and uniqueness are two different phenomena. Okay. Now let us move forward for system of first order equation, and we try to discuss the existence and uniqueness theorem which we have developed for scalar differential equation for the system of first order equation. So here we are looking of a system of first order equation. We now wish to consider the extension of existence and uniqueness theorem to system of first order equation of the form y dash equal to f t y. So here this represent what? Here y and f are vectors with n components and t is a scalar. So I can write this as the following. So here we have y dash equal to f t y. So here this y is a vector of dimension n cross 1. Similarly your f is also a vector of n cross 1, and we can write this as y1 dash equal to f1 t y1 y2 and yn here. Similarly y2 dash equal to f2 t y2 y1 y2 and yn and so on. So it means that this y dash equal to f t y represent this system of first order ordinary differential equation. So here we can write this y1 to yn as y here. So it is n cross 1 here. Similarly we can write f as f1 and so on fn. So here if we use the vector notation as this, then we can write down this system of first order equation as y dash equal to f t y. So that represent the system of first order ordinary differential equation, and here we assume this condition that let f be a continuously differential with respect to t and with respect to the components of y at all points of d, and suppose that there exists a constant k greater than 0 such that the norms of del f by del y j satisfy this following condition. So here to get that existence and uniqueness theorem, we talk about the first theorem which we have discussed, which is known as Picard iteration scheme. So to generalize that, we assume that f is a continuously differentiable function. So here we assume this first thing with respect to t and with respect to the component y of. So it means that here del f by del y j t y is less than or equal to k. Here this represent norm. I hope that you are aware about this function norm. It is a generalized distance function satisfying certain condition. So we are using this as a norm here. So so if we have these condition, then we can say that then f satisfies the Lipschitz condition in D. So it means that here we are assuming that a partial derivative of f exists with respect to the component yj and it is bounded. Then we can say that it satisfies then it guarantees that the function f satisfy the Lipschitz condition. And how we can guarantee that? Here we can write we can define a new function g sigma which is given as f t z plus sigma y minus z, and if you look at this is defined as one variable of sigma. Here if you put sigma equal to 0, then it is nothing but f t z, but if you take sigma as 1, then it is nothing but f t y. So with the help of g sigma we define this value this f t y minus f t z as g1 minus z0. So this g1 minus z0 is given by 0 to 1 z dash sigma d sigma. So using mean value theorem we can write g1 minus z0 as 0 to 1 g dash sigma d sigma, and by the chain rule we can find out g dash sigma as this. So here we use a notation f yj equal to del f by del yj for j equal to 1 to n, and we can write g dash sigma as f y1. Here we are using finding the derivative of g sigma with respect to sigma. So, here we can write Fy1 t z plus sigma y minus z and multiplied by y1 minus z1 plus Fy2. So, here partial derivative of with respect to y2, argument is same y2 minus z2 and so on. So, here we can write norm of Fty minus Ftz is equal to 0 to 1 g dash sigma d sigma, and g dash sigma is given by this quantity. So, we can write this as, since Fy1 this is bounded by k, this is bounded by k, and all these are bounded by k. So, we can take it out, and what is left here is modulus of y1 minus z1 plus modulus of y2 minus z2 and so on, and this we can say that this is nothing but y norm of y minus z. Here we are using one norm of y. So, here we define what is one norm of y. So, one norm of y is given as if y is given as y1 to yn, then one norm of y1 is given as modulus of y1 plus modulus of y2 and so on modulus of yn. So, here we are using one norm, and we can say that modulus of Fty minus Ftz is less than or equal to k times y minus z, and which says that function Fty satisfies the Lipschitz continuity Lipschitz condition in the variable y. So, it means that if we assume only this condition, that partial derivative exists with respect to component of y and it is bounded, then f satisfies the Lipschitz condition, which is verified here. So, now we define the theorem that let f and double f by double yj be continuous on the box B Ty, where modulus of t minus t naught is less than or equal to a, and norm of y minus eta less than or equal to b. Here eta represent the initial condition y at t naught, where a and b are positive numbers and satisfying the bound modulus of Fty is less than or equal to m. Here it is norm of Fty is less than or equal to m, and norm of double f by double yj is less than or equal to k for Ty in b. And here let us take the alpha be the smaller of the number a and b by n, and define the successive approximation as we define in theorem 1, phi naught t as eta and phi n t as eta plus t naught to t, fs phi n minus 1 s ts. Then this sequence phi j of successive approximation converges uniformly on the interval modulus of t minus t naught less than or equal to alpha to a solution phi j of 5 that satisfies the initial condition phi t naught equal to eta, and the solution is given as we have done in case of theorem 1. The only thing is that here modulus is replaced by norm. So, here we have not given emphasis on this, this represent norm in vector case. So, it means that theorem 1 you can exactly write it here. The only understanding we have to assume that this is not a modular sign, this is a norm in n dimension. So, and similarly we can define the uniqueness of solution. So, our next goal is to prove the that under suitable hypothesis there is only one solution phi of differential equation y dash equal to Fty with the initial condition phi t naught equal to eta, and here the condition is Lipschitz condition. So, suppose f and double f by double yj, j from 1 to n are continuous on this rectangle B, then they exist at most one solution of 1 satisfying the initial condition 12. So, here we can say next theorem that suppose f is continuous on the rectangle R, which is defined like this, and monotone non increasing in y for each fixed t on the rectangle R, then the initial value problem has at most one solution on any interval j with t naught as left hand point. So, here we have discussed this theorem, that is existing theory for system of first order equation, that if f is continuous differentiable and satisfy this equation number 6 that partial derivative exists and bounded by k, then solution exists, and not only the solution exists, it will have a unique solution, that is given by uniqueness of solution. So, the same condition is also true for having existence of unique solution of this. And if we assume only the continuity part, then we have one solution of the system. So, here we will take just one quick example, and here we look at the problem y dash equal to GTU, GTY here, and and here y is given as y1 and y2. So, it is in 2 dimension, and we want to find out that here this gxu, which is defined as a11 u1 plus a12 u2 comma a21 u1 plus a22 u2, then this function g is actually satisfying the Lipschitz condition. Here we are not applying the result that partial derivative exists with respect to the component. Here we can use other method to show that it has a it satisfies the Lipschitz condition. For that, just look at norm of gxu minus gxv. Now, what is gxu? Gxu is given by this minus gxv, we also put it here. So, it is norm of a11 u1 minus v1 plus a12 u2 minus v2 comma a21 u1 minus v1 plus a22 u2 minus v2. So, here we can simply write that this is less than or equal to, here we define the norm y as one norm. So, norm 1 as y1 plus y2 modulus of this. So, using one norm we can write this as this is nothing but modulus of a11 u1 minus v1 plus a12 u2 minus v2 plus here we are using one norm modulus of a21 u1 minus v1 plus a22 u2 minus v2. So, and this is less than or equal to same quantity, you can write it, and here if we write it a11 plus a21 then multiply u1 minus v1 plus this quantity multiplied by u2 minus v2. So, if we take the maximum of this quantity and this quantity, or you can say maximum of modulus of a11 plus a21 comma a12 plus a22, then we can write it modulus of u1 minus v1 plus u2 minus v2, and if you look at this is nothing but the one norm of u minus v. So, it means that we can write that here this is less than or equal to maximum of a11 plus a21 comma a12 plus a22, then norm of so one norm of gxu minus gxv is less than or equal to k, which is denoted by this maximum value times u norm of u minus v. So, here what we have shown here is the following thing, that gxu minus gx v one norm is less than or equal to k times u minus v one norm, and one norm is defined like this, that it is the sum of the absolute value of the component. So, here we have shown that G satisfy the Lipschitz condition in one norm, and here we have to note down one important thing, that in Rn here let me write some result, that here in Rn all we can define several norm. So, let me write it a few norms. So, first of all, what is norm here? Norm is basically a function from R n cross Rn to say R plus union singleton 0, and it satisfies certain properties, that is norm of x is greater than or equal to 0. So, this is one property. Another property is that norm of x minus y is same as norm of y minus x, or you can say that norm of alpha x is given as modulus of alpha norm of x here, and it satisfies one more important property, that norm of x plus y is less than or equal to norm of x plus norm of y. So, it is a generalized distance function we can say, and in Rn we can define several norms, and the common norm is norm 1, that is if we look at x as x1 to say xn, then one norm is given as modulus of x1 plus modulus of x2 and so on modulus of xn. So, this is one norm, and you can define two norm like this, that it is under root of x1 square plus x2 square and so on, and infinity norm, which we can say that it is supremum of xi and I is from 1 to and n. So, here we can say that we can define several norms 1 to infinity. Here it is true for all, right, and here we can also discuss that why this system is important, why we have written only for system of first order equation, because if you look at any nth order differential equation, say yn plus an yn an minus 1 yn minus 1 an minus 2 yn minus 2 and so on. So, here we can say that if you look at any this nth order differential equation, here this an's may be functions. So, here an's ai's an minus 1 and so on, all these are maybe function or maybe constant values. So, we can say that this can also be written in system of first order equation. The only thing we have to observe that x1 is, let us say, y, and x2 is y dash, and so on. We can define xn minus 1 as y, x1 is y and x2 as y dash. So, xn minus 1 is yn minus 2. So, xn is given as yn minus 1. So, here we can write this as, say, x1 dash is basically y dash, so which is nothing but x2. So, x2 dash is y double dash, that is nothing but x3, and so on. We can define xn minus 1 dash is equal to yn minus 1, that is given as xn, and xn dash is given as yn, and this is this you can write it minus 1 upon an, provided that this an is non-zero, and you can write down this as this an minus 1, yn minus 1 is given as xn minus plus an minus 2 and xn minus 1 and so on. So, here we can simply say that this I can write it here as x1 to say xn dash is equal to, now here what we have written, x1 dash is equal to x2. So, it is x2, x3, x4 and so on. Here we have written minus 1 upon an and this thing, and if you further simplify this, you can write this as x1 to xn, and here we can write down 0 1 and so on, 0 0 1 and so on. So, I request you to complete this, that any nth order differential equation with the coefficient may be constant, may be function, can be written as x dash equal to this thing, and we can write that it is a particular case of this quantity. So, it means that if we know the existence and uniqueness theorem for this system of first order equation, then we know existence and uniqueness theorem for this. So, it means that here we have assumed that our function f t x is continuous with respect to x. So, here we say that f t x is nothing but coefficient here. So, here if coefficients are continuous, then by existence and uniqueness theorem for system of first order equation, we say that it will also have a solution. And similarly, you can consider any nth order equation yn equal to f t y y dash up to yn minus 1 to again system of first order equation, that is x dash equal to f x comma y. Idea is same, that you assume x1 as y, x2 as y dash and so on. So, here we have xn as yn minus 1, and you can write down x1 dash is equal to x2, x2 dash equal to x3 and so on, xn dash is equal to yn, that is given as your f, and here it is what t, and it is x1 to xn minus 1 here. So, you can simplify this and you can write x1 to xn here, derivative is equal to, now here we can define this as x1 sorry x2, x3 and so on, at last here we have x1, x2 and so on, and this you can call as f t x. So, it means that any nth order nonlinear differential equation as well as linear differential equation with the constant coefficient or variable coefficient can be written as system of first order equation, that is x dash equal to f dx. So, it is sufficient to discuss the existence and uniqueness theorem for system of first order ordinary differential equation. So, we in this lecture we have discussed several things, that how the existence and uniqueness theorem given for scalar equation, a scalar differential equation can be generalized for system, and with this we may cover the all the ordinary differential equation, whether it is single scalar first order, second order or nth order. So, here we have said that if it satisfies the ellipsis condition, then we have a unique existence and uniqueness both. If it satisfies only the continuity, then it has a solution, it may not be unique, but if it satisfies one more condition, that if function f is satisfying the continuity as well as the monotonically non decreasing condition, then it will have a unique solution. So, here with this we stop and we will discuss new things in next lecture. Thank you very much.